Welcome back to my channel, Predicting the Future. Today, we're going to talk about existence of stationary distribution in Markov chain. We're going to see under what condition does a stationary distribution exist. We're going to try to construct a stationary distribution. Let Xn be the Markov chain. What stationary means is that the probability of the Xn equals to some state I doesn't change over time. That means that the probability of Xn equal to I is equal to probability of Xn plus m equal to I, or for any m. So that's the basic idea of stationary distribution. Think about the Markov chain. It's the state machine. It transits from one state to another, and so on for infinite many times. So under certain conditions, the process will be in state I with the fixed probability distribution. So that's what it means stationary. It means stationary over time. So that let's see the definition officially. So stationary or stationary in time it basically means that the joint distribution of certain array of random variables in the Markov chain process doesn't change if we shift those joint random variables to another time. So that's the stationary. What is stationary distribution? So let's first look at the stationary. So we know that stationary means that the probability of xn plus 1 equal to I equals to probability of xn equal to I. Then let's first expand the probability of xn plus 1 equal to I. We can write it as a summation by conditioning on the probability of xn equal to j over all the state j times the probability of xn equal to j. So that summation actually equals probability of xn equal to I by the definition of stationary. But the probability of xn plus 1 equal to I, given the xn equal to j, is actually the ij entry of the Markov chain transition matrix. So look at the red equation here. We can basically write it as the probability of xn equal to j times the next transition of pji, which is transition from state j to I. And so stationary distribution tells us that this summation p probability xn equal to j times pji is actually equal to probability of xn equal to I. And if you look deeper, trying to understand this equation deeper, you know that when we try to sum this, look at the left side, the summation, it means that we don't care where the previous state is, which is state j. We don't care where they are, what the value of j is. The probability of entering state I is a constant value, which is the probability of xn equal to I, right? So that's the stationary distribution. And it's true for all n. It's true for all n. And and because of the xn plus 1 equal to j equals xn equal to j, the probability is for all n, then we can basically give a easier notation that's called pi j, which is a constant value for all n. Then we can write the red equation here into summation of pi j times pji equal to pi I. So that's actually the definition of a stationary distribution. So let's look at the official definition of stationary distribution here. What we just saw, the summation of pi I times pij equals pi j, which is what we just saw. We derived that formula using the stationary definition. But it's a distribution, so the pi I, the summation of pi I must equal to 1, right? No matter where we are in the previous state, which is pi I could be from 0 to infinity, or 0 to some value n in this specific Markov chain process. So previously the Markov chain must be in some other state and transitions to state j. And this is actually defines the probability of pi j, which is the probability of that process is at state j. So what it also tells us that this is, if this summation is, if we look at it, it's actually a multiplication of a vector times a matrix, the transition matrix P. So we can write it as pi times P, vector pi times matrix P equals to pi. And by induction, which also tells us that vector P times probability times the matrix P to the power n is still pi. So what does that mean? After n steps, the transition distribution doesn't change. Let's say pi is the initial probability of the initial probability p x0 equal to I for all I. That's the vector pi I. Then after n steps, so that will be pi times matrix P to the power n, and by the definition of Markov chain, that's actually the probability of xn equal to some state I, given the x0 equal to some other state. So this is a constant value pi, constant vector pi. It doesn't change. So after n steps, the probability doesn't change. So this is actually what it means by stationary distribution. But the problem is, under what condition does a stationary distribution exist? In many cases, it doesn't guarantee a stationary distribution. Well, we will see that in the future. But if you ever watch my previous video when I was talking about a random walk, if let's say the random walk in one dimensional and it's the probability of going right to the left is now equal, so it's now 1/2, then we have proved that this is a transition chain. If it's transition, there's no way to have a stationary distribution, because after some time the process will never return back to certain states. Let's say state 0, then we know, so that's the probability will never be the same after n times, after n plus 1 times. So the distribution then changes over time. So let's first construct a stationary distribution in an intuitive way. Suppose state I is a recurrent state, then which means that we will always return back to state I after finitely many times. If we look at this process, random process, if we simplify this random process, we look at the transition as a constant. It's not a random process, it's a fixed process. State I will always return to state I after a fixed number of time, let's say n. So I will be back to I in n times. And during that period, in the middle of that process, other states, let's say state j, state k, and so on. And so the probability, if we define the probability, let's estimate the probability of xn equal to j, or within that period. So it sounds, it looks like a pretty reasonable guess that, let's say, in that one period of I, there's two j occurred in this process in this one period, then the probability of the stationary distribution of j might be 2 over n. It sounds like a good way of estimating the stationary distribution of xn equal to j. So let's see if this is a good guess. So let's officially define that intuition here. So let's define mu I j, which is the expected number of visits to state j in one period of I returning back to I. So that will be the expected value of condition on the initial state is I, on the summation of all the process xn equal to j until ti, which ti is the time of xn back to state I. So summation from 0 to ti minus 1 of the identity random variable f on xn equal to j. So this is actually counting the expected value of the process that enters state j in that one period of I returning back to I. And if we do a conditional, so let's see if we can find a simplified equation of that expression. So let's condition on the ti. So condition expected value of ti on expected value I of that equation is actually two summations. When ti equals to m, where m is from 1 to infinity, times the summation of n equal to 0 to m minus 1, where the m is actually ti. When we condition on ti equal to m, that ti on the summation becomes m minus 1, not ti minus 1 anymore. We know that constant value now. Times the probability of pi xn equal to j and ti equal to m. So that's how we that's the double conditioning and double expectation. And because it's a posterior series, by the Fubini theorem, we can switch that equation. We can switch the summation, move the summation of m inside, move the summation of n outside, change the variable. We get this one, and when we sum of m equal to n plus 1 to infinity, that's actually ti greater than n. So that eventually simplifies to the summation of n equal to 0 to infinity pi xn equal to j ti greater than n. So that's a much simplified way of expressing the expected number of times that process enters state j in one period of I returning to I. And mu ii is 1, right? So why it's so write down the equation we just simplified. That's actually a summation of the series of x pi x0 equal to I, ti greater than 0, plus pi x1 equal to I, ti greater than 1, and so on. But if the first term is actually 1, the pi x0 equal to I, ti greater than 0, which is for sure is 1, right? Because if initial x0 is I, then the first term is definitely 1. We already know by the conditioning x0. But the second term and third term and so on are all 0, right? Why? Because if x1 equal to I, given that ti greater than 1, which is impossible because x1 is already 1. Ti could not be greater than 1. Ti should be equal to 1. Same for x2 equal to I, and so on. So all the terms behind that is all 0. So mu I is 1. And let's further look at the summation of the mu I over j, which is summation of this term. And this is actually summing over so this is actually two summations, summation over j and summation over n. If we switch the summation, same by the Fubini theorem, so we can do the summation over j. It's all over j. So the joint probability of xn and ti will simplify to only probability of pi, ti greater than 0. So xn equal to j is gone. And that's actually the definition, well, not the definition, but the same way how we can define another way of defining expectation of ti. We saw this is also using the Fubini theorem. We talked about that in the previous video series as well. So if you never see that before, you can go back to the previous videos. This is actually the same thing. So because of that, we know that mu I itself, this function mu I, has a very good property. It looks very similar to a stationary distribution, rather than it's not a probability. It's just a expected value. But if we can divide that mu I by because the summation of mu I is just expected value of ti, then if we can divide that mu I by expected value of ti, then this becomes a probability distribution, right? If we sum over this term mu I divided by ei ti over the summation over j, this is actually 1, right? So that sounds like a potential candidate of stationary distribution. So here's our so that comes to a theorem we want to prove from the intuitions we just talked about. So the theorem is if I is recurrent, we need I to be recurrent to be able to define mu I, right? So that's how we define the mu I in the previous talks. If I is recurrent, then mu I satisfies mu I p equals to mu I. That's something we want to prove. So this looks very similar to stationary distribution, like what we just talked about. If we can divide mu I by the expected value of ti, that becomes a stationary distribution. The vector mu I times matrix P equal to mu I is if it's expanded, it's a matrix multiplication. If it's write as a summation of series, that becomes mu I on value j times pjk equals mu I k. So that's the vector mu times the kth column of the transition matrix, and that gives us the kth item of the new vector. So mu ij over eiti is a solution that satisfies the definition of a stationary distribution, because by the theorems above, it already satisfies mu I p equals mu I. And if we divide the whole term by eiti, it will satisfy the other condition of summation of pi j equal to 1. So now let's prove this. Let's prove this theorem. So this theorem is we want to prove mu I times matrix P equals to mu I, or summation of mu ij times pjk equals mu I k. So that's something we want to prove. Let's suppose that k. Let's split that into two steps. First part is when k is not equal to I, and the other part is when k equal to I. When k equal to I, we know that mu I k, which is actually mu I, is 1, which is a simpler way that we can prove. So let's leave that in the next step. Let's first look at when k is not equal to I. So when k is not equal to I, the summation of mu ij times pjk, let's put in the formula we just got for mu ij into this formula, and that becomes a joint distribution. That becomes what? That becomes so there's two summations over probability p on initial condition I of xn equal to j, ti greater than n, times pjk. And what is that? So we know the previous step is xn equal to j, and next step is j transition from j to k. And then that's actually by the definition of matrix of Markov chain. This is actually the joint probability of xn equal to j, xn plus 1 equal to k, and ti greater than n. Same here, we use a Fubini theorem. We also switch the summation of j and n. We move the j inside and outside. That is, we summing over the j over all the j. So the term xn equal to j in the probability here, the joint probability here, were gone. So xn was gone. That becomes the summation of n equal to 0 to infinity probability pi xn plus 1 equal to k, ti greater than n. But pi xn plus 1 equal to k, ti greater than n can be, we can expand it to change the xn plus 1 to xn, because when n equal to 0, the probability pi xn equal to k, ti greater than 0 is actually 0. Why? Because if ti is greater than n, given the initial condition of x0 equal to I, then x0 equal to k is just impossible, which is 0. So that eventually gives us the result of mu I k, which is what we want, what we are trying to prove. When k is not equal to I, so when k, we already proved when k is not equal to I. Now the last thing we need to prove is when k is equal to I. So when k is equal to I, the same way we expanded, we put the formula of mu ij into this summation, and that becomes the same thing, the pi xn equal to j, xn plus 1 equal to I, ti greater than n. Summing over j over, so the xn equal to j term is gone. Only what we left is n equal to 0 to infinity pi xn plus 1 equal to I, ti greater than n. But this probability given I, the probability of pi, initial value is equal to I, of xn plus 1 equal to I, ti greater than n, is actually ti, probability of ti equal to n plus 1. Why? Why? Because xn plus 1 equal to I is already meeting the event of ti greater than n. Ti, what is ti? Ti is the first time the process returned to I. Right? Starting from I, the first time returned to the I. But this condition is probability can tell us that the first time returned to I is actually xn plus 1. So that becomes probability of ti equal to n plus 1. We sum over them, that's actually probability ti less than infinity, which is 1. And that's actually mu I.